This lecture will concern plane curves and parametric equations, including a small bit of motivation, the definitions involved, and a quick example of sketching the graph of such a curve. Oftentimes we have been dealing with or studying curves on the two-dimensional Cartesian coordinate plane, the xy plane, if you will, where y is a function of x. Namely, we oftentimes write y equals f of x. Any point on that curve is described both by an x and a y coordinate, and since y is equal to f of x, we could describe the point as x comma f of x. Uh, in the real world, it oftentimes becomes beneficial to have a third variable involved. So suppose that you have your Cartesian coordinate plane, and you consider a point moving around in this Cartesian coordinate plane, some sort of particle, maybe an electron or some other sort of particle. Well, that particle may move in some kind of crazy ways, and so the particle may start at this point and move along this curve this way, so on. And this curve no longer defines a function of y in terms of x. We can quickly notice that because of the vertical line test. If you, for instance, choose this vertical line, this hits the curve in more than one spot, and so this curve is not a function of y in terms of x. However, the y and x variables themselves may be functions of a third variable. So you can consider, what if you consider y as a, x as a function of, say, a third variable t, and y as another function of, again, of that third variable t. And sometimes we consider this variable t as time. So let's quickly make a definition. Definition: if f and g are continuous functions of t on an interval I, being the closed interval from a to b, say, then the equations x equals f of t, y equals g of t are called parametric equations. And t, the variable t, is called the parameter. So again, t will oftentimes be referred to as time. And so in our graph above, you could think of this particle moving along this graph with respect to time in the direction given by the arrows. And so at any certain time t, the coordinates of the point would be f of t, g of t, because x is equal to f of t, y is equal to g of t. The graph and equations together are called a plane curve. You could use the words plane curve more generally to describe any curve in the two-dimensional Cartesian coordinate plane, but we use it here specifically with respect to parametric equations. And sometimes we could say it's a parametric plane curve, but oftentimes we'll just say plane curve. And we denote a plane curve. We could use the letter C or some other letter, capital letters. If, sorry, not if, the points f of A, g of A, and f of B, g of B are called endpoints of the graph. Remember that A and B are the bounds on our interval I, where these curves obtain their parameters. So T ranges in this interval from A to B, and if we put A into F and G and get a point, and we put B into F of T and G of T and get another point, those are called the endpoints of the graph. If those 2 points are the same, in other words, if they are the same point, they're equal, then we call the curve a closed curve. If the curve is a closed curve, with no self-intersections, in other words, the curve does not cross itself, then we call it a simple closed curve. So just to look at a couple of potential graphs. Here's a plane curve. I've omitted the x and y axis just for clarity. If you're considering this a curve where a particle moves along the curve, obviously it would start here at this point, and this point would be one of our endpoints. So this would be f of A, g of A. And the point could travel along the curve in the direction of the arrows, and that would be exactly as the variable, the parameter t, in the interval from a to b ranges from a to b. So we make t range from the smaller number, in this case would be a, and it ranges in an increasing fashion up through b. So that would mean that the final point on this end of the graph would be f of b, g of b. So f of a, g of a, f of b, g of b are the endpoints of the graph. And since the endpoints are not equal, this is not a closed curve, and hence it's also not a simple closed curve. Another example of a plane curve maybe something like this. Here, the initial point, f of a, g of a, is equal to the terminal point, f of b, g of b. So this curve is a closed curve. Notice that apart from the endpoints, the curve does not intersect itself. So in fact, this is a simple closed curve. And finally, we could have maybe a slightly more complicated example. And I'll just put a few arrows to indicate the direction of movement. Perhaps I made this curve a little too complicated. The endpoints are the same, f of a, g of a, and f of b, g of b. So this is a simple closed curve. It is a closed curve, excuse me. However, it certainly intersects itself in many points, so it is not a simple closed curve. One thing that we would like to do is we'd like to be able to sketch the graphs of some of these plane curves. So suppose that we are asked to sketch the plane curve defined by x equals the square root of t and y equals 1 minus t, with t ranging between 0 and 4. One way that we can accomplish this is we can pick various values for t that are between 0 and 4 inclusive, and we can substitute them in for t into our equation of x and our equation of y, and we can get coordinates. So this means that we could do a table. So let's take this to be t, this to be x, and this to be y. So in this case, we are told that x is equal to the square root of t and y is equal to 1 minus t. T is between 0 and 4. So let's pick some values for t. Let's say 0, 1, 2, 3, 4. There's nothing super special about these values for t. We just need to make sure that they are included in the interval. And in this case, that interval is from 0 to 4. So we can go over on the side and we can do some calculations. So if t equals 0, then x is equal to the square root of 0. Excuse me. And y is equal to 1 minus 0. In that case, x is equal to 0 and y is equal to 1. So we can put those in. X is 0, y is 1. If t equals 1, then x is equal to the square root of 1. Y is equal to 1 minus 1. So we are simply taking our values of t and substituting them in for t into these equations to get our coordinates x and y. So x is 1, y is 0 in this case. And in this way, we could fill out the rest of the table. So for instance, if t is 2, then x is the square root of 2. And y is equal to negative 1. If x is 3, then if t is 3, then x is the square root of 3, and y is equal to negative 2. If t is 4, then x is the square root of 4, which is 2, and y is equal to negative 3. Once we get our table filled out, we can plot the points on the Cartesian coordinate plane. So we have the point x is 0, y is 1. So we have 0, 1. We have the point 1, 0. We have the point the square root of 2 and negative 1. Remember that the square root of 2 is approximately 1.414. It's an irrational number, so we could keep going as long as we wanted to. So the square root of 2, negative 1. Then the square root of 3, negative 2. Square root of 3, remember, is about 1.7. Again, it's an irrational number, so it continues on. And finally, 2 comma negative 3. I have taken a moment to pause and make our graph a little bit bigger so we can see a little more what's going on. At this point, we have our 4 points, 0, 1, 1, 0, square root of 2, negative 1, square root of 3, negative 2, and 2, negative 3. If we connect the dots with a smooth curve, there's our curve. Now remember that all of these, this x and y, they depend on the parameter t. And if you're thinking of t as being time, you can think of this curve as a particle moving. And so the particle would start at the point 0, 1 and would travel down the curve this way. So we can put some little arrowheads there to indicate what we call orientation. Unfortunately, when we sketch our graphs, we lose some of the information. Notice we still do have the x and y coordinates, 0, 1, 1, 0, and so on. But on the graph itself, we don't have any indication as to what t is, or even the interval upon which t ranges. However, we can put the orientation to remind us that when this graph starts at the point 0, 1, so we could say this would have to be t equals 0, and then if we knew that our interval was from 0 to 4, then we would know that this bottom point, 2, negative 3, is where t is equal to 4. Now we could label each point with its corresponding t value, but that makes the graph jumbled. And so we often just provide the orientation to allow us to know how the graph would flow. So this is an example of sketching a plane curve given by parametric equations in the xy plane.